Hello, my name is Musab Kasbati and I'm joined by my partner Raahim Hashmi. And for our graph theory project, we'll be going over the recent paper on breaking the sorting barrier for single source shortest path problems. In particular, this paper provides an algorithm that runs in m log 2 to the third n, where m is the number of edges in the graph and n is the number of vertices in the graph. And this is actually faster than any known deterministic algorithm for sparse graphs, that is, when m is not much larger than n. Now, the way we'll go over this is first we'll give some of the motivation, maybe a story behind where this algorithm can be used. Then we'll dive into the formal definition of the problem, then the actual algorithm with its inputs, outputs, pseudocode, correctness, and time complexity. And at the end, a few comments or critique on the algorithm itself. So here is a possible story, a possible scenario where you'd want to use this. Ashraf is very late for his project presentation, and he must identify the shortest route to university to arrive on time. Luckily, he knows that each intersection has at most 4 nodes going in and out of it. How can he leverage this information? Well, the key thing here is that if we think of the road network as a graph, then we have that each intersection has a degree of at most 4, which means the number of edges we have is actually not that much larger than the number of intersections we have. And in that sense, the graph is sparse. And we actually see sparse graphs occur in many real-world scenarios, especially when we talk about physical planar space. Then the graph has to be sparse. Now, how's the algorithm defined? Let's dive into that. So in this particular case, we will define the single source shortest path problem as that given a directed graph G with a set of vertices and a set of edges, and each edge has a non-negative real weight, then we want to compute DSV, that given a source S, DSV represents the shortest path distance from S to a vertex V, and we want to do this for all vertices V. Now, the assumptions for our graph is firstly, one important critical assumption is that all path lengths from S to V are unique. This makes it so that we have no issues in ordering and defining what we'll later call boundaries. The other thing is that all vertices need to be reachable from S, so the graph has to be, in a sense, not just connected is an undirected term, but connected from reachable from S, right? And the other thing is we focus on constant degree graphs with a bounded in and out degree. And what exactly is a constant degree graph? So let's think about families of graphs. So let's talk about a cyclic graph. Here you see that every node has an out degree of 1. So this is like a constant degree because the degree is 1. But if you talk about the family of complete directed graphs, the number of edges from a particular node are n. And so this is order of n degree. It is not constant degree. And this sort of goes back to that idea of a sparse graph. Now, as for the preliminaries, we let dv represent the actual shortest path distance, and we have d hat v represent the algorithm's current estimate. And if we ever get that d hat v equals dv, then that means that the node AV is complete. We found its shortest path. Similar algorithms which have been previously known and used are Dijkstra's algorithm, which uses a priority queue, it extracts the vertex of minimum estimated distance, and relaxes the edges going out of it. It implicitly then is sorting all of the nodes by distance, because again, it has to repeatedly extract a minimum. This means it faces the comparison-based sorting lower bound of omega n log n, so it can't go any faster than that, and its time complexity is generally cited as theta of m log n. If we talk about the Bellman-Ford algorithm, this repeatedly finds paths of increasing edge lengths. So first it finds the shortest paths using only 2 edges, then 3 edges, then n edges, by repeatedly relaxing all of the edges for a series of n rounds, or order of n rounds. Now, this doesn't require sorting, but it has a harsher runtime of big O of nm. Now we'll introduce a somewhat related but more general problem called the bounded multi-source shortest path problem. And this is what the paper focuses on, that for a graph, we are given a set of sources, so not a single source, but a set of sources. In this case, you have these 3 yellow nodes, and each has a distance already associated with it. So this has 0, this has 1, and this has 5. And we're given a boundary value b, which in this case is 10. And what that means is that for all nodes which have an actual distance from these sources, which is less than b, then we need to find dx. Now here, since the boundary is 10, and actually all nodes have distance less than 10, so everything falls within the boundary, and we have to find shortest distances for everything. And you can think of it this way, that if I replace the set of sources to just a single source S, and I set my boundary b to infinity, then this is just the single source shortest path problem. So this is actually a more general version of the single source shortest path problem. Now, a way we can do this is that we take all of our sources and their distances, and we put them in a priority queue based on their distances. And then, as per Dijkstra's algorithm, we extract the node with the least distance, and we relax the edges out of it. And in fact, this would work. This would be great. But the issue here is that this would require all nodes to enter the heap, which means all nodes are going to implicitly be ordered, which makes it slow. We're going to run into the lower bound. So we're going to try to speed this up with a different approach. And so we'll focus on the divide and conquer paradigm. So in the divide and conquer paradigm for this problem, what we can do is, instead of solving for the boundary 10, what if we first solve for the boundary up till from 0 to 4, and we solve for the boundary from 4 to 10, right? And okay, let's say that you actually do for a boundary of all nodes with distance less than 4. Now, when I want to talk about the nodes with distance between 4 and 10, the issue is when I'm talking about shortest paths, I have to consider shortest paths starting firstly from sources that have a value larger than 4, but I also need to consider paths starting from the previous boundary, like from the left of the boundary and crossing over. And the way to do that is I actually, once I know the distances which are less than 4, I can relax the nodes to the left of my boundary to actually get the values of things to the right of my boundary. And this actually creates a new source in this case. I get this source of distance 4, and then I solve the bounded multi-source shortest path problem with a source 4 and a source 5, and these edges and a boundary of 10. All right, so then we can actually solve the problem, but we needed to first compute this. Okay, and we created new sources. And if we talk about the individual problems themselves, they feel too big. The nice thing about divide and conquer is you can just keep dividing until you even get down to a problem size of 1. And what that means is, okay, just solve the first boundary, which there's nothing to do. Then you just relax the edges out of it. And then from the least of the vertices next, you relax its boundary by just processing that node. And this could be like an alternative approach to actually shortest path finding. And this is actually turns out to be the same as Dijkstra, but this is a cool thing that you can do. But there is a downside to this, that to actually divide into single nodes per subproblem, that requires actually ordering the nodes in a sense, because you need to know what's the first boundary, what's the second boundary, and so on. So that's going to run into your sorting lower bound as well. And the other thing is, if we did not shrink our subproblems all the way down, but only a little bit, then if we still use Dijkstra for the larger subproblems, then the issue is that everything eventually enters our heap. So things to the left will enter the heap, but things to the right, this thing which was not a source, it will now become a source and will join the heap. So everything will get ordered this way. And so if since everything becomes a source, that becomes a bit problematic. What if we could reduce the number of sources we have? Because that could potentially speed things up.
All right, we want to cut down on our sources and we want to identify a set of pivotal sources, let's call them pivots, such that we can treat these set of pivots as the new sources and we can still solve the boundary multi-source shortest path problem. We want an algorithm that spends less time identifying these pivots than it would have taken to just work with the original set of sources. Keep in mind that in the worst case, the set of sources can be at most the size of all of the nodes in the subproblem. You get to lemma 3.2 in the paper. It says that okay, okay, you're given two integer parameters k and a bound b, and you're given in the set of initial sources s, and you tilde which is a set of all vertices with their true shortest path distance being less than b and the shortest path passing through some source, which is a very long way of saying that you tilde the set of all vertices in a subproblem. For example, in this graph that we saw before, the nodes in red are the sources. All of these nodes on the right side are the are u tilde, the bound being b equals 10, and then k can be some integer parameter that we set. The lemma says that there exists an algorithm that outputs two things. First, it outputs a set W, which is a subset of the subproblem of size at most k times size of the set of sources, and it outputs a set of pivots as well, which is a subset of the set of sources, and it has size at most 1 over k times the set of the size W, um, which itself can be at most the size of the set of all vertices in the subproblem. Such that for all of the vertices in the subproblem, at least one of the following condition is true: either that vertex is in W and it is complete, so its shortest path distance is identified, or its shortest path passes through some pivot that we've identified. Um, so it's saying that there is an algorithm that does two things for us. Not only does it identify a set of pivots, it also solves completes some vertices along the way. It also says that this algorithm runs in big O of k times the size of set W, and that works out to be minimum over k squared times the size of set S and k times the size of set of the subproblem. Um, so before we even get to the algorithm, let's think about how this may help us. So we are saying, okay, we're not completing every vertex in the subproblem, but we know that every vertex that is not complete lies on the shortest path tree rooted at some pivot that we've identified, which is this second condition here. So we can only consider these pivots as the sources, and then we're good. However, and also not only that, this set of pivots is 1 over k times the size of the entire subproblem. So our set of possible sources has been cut down by 1 over k, and we've only done some k square times s work, additive work, to identify these pivots. Let's see how this can work out for us. Let's set k equals to log n to the one third. If we have the set of sources be all of the nodes, so set of size of the set of sources is n, and we are going to do log n work for each possible source. Our total work is going to be out of n log n, because it's n sources, log n work for each source. However, if we identify the set of pivots first, so the size of the set of pivots is going to be n over k, where k is log n to the one third. We're going to do log n work for each pivot. And in identifying these pivots, we've done n times k square, where k square is log n to the two thirds work. Our time complexity actually works out to be n times log n to the two thirds, which is clearly less than n log n. So there's a lot of promise to this algorithm, as it is helping us cut down our time complexity. Let's give you some basic idea of this algorithm. This algorithm starts off by doing k Bellman-Ford like relaxations that radiate outwards from a set of sources. So we know that if you run Bellman-Ford relaxations k times, you're going to identify all k as shortest paths. So any nodes that are and we're going to do this Bellman-Ford from the set of sources. So any nodes that are within k edges from the set of sources will then be identified. Will then be actually complete. The shortest paths will be identified. Um, any vertices that are not completed will have a shortest path tree rooted at some source, and this shortest path tree will obviously have more than k vertices, or at least k vertices. Then we can identify all such sources that are the roots of such of the shortest path trees with more than k edges, k nodes, and then these can become our pivots. To illustrate this idea, suppose this is a subproblem where all of these nodes are utilda, and the set of sources is a, b, c, and d, and k is set to 2, and the bound is set to 10. We first run Bellman-Ford k equals 2 times, so we identify all two shortest paths, which you can verify is the case here. Identify the paths in maroon. Then we have these shortest path trees. We have four shortest path trees here, A, B, from A, B, C, and D. We're only going to keep those trees, those sources as a pivots that are the roots of trees with at least k nodes. Not counting the source. So from our four sources, only two sources are the roots of such trees, and these became our pivots. So we are saying, okay, to solve the rest of to find the shortest path in the rest of the subproblem, we can only we need to only consider these two nodes, and do our work from these two nodes, and we don't need to consider the nodes A and D. Moving towards the pseudocode, as I said, so it starts by running Bellman-Ford and radiates outwards. So it's going to start by relaxing all the edges from the set of sources. Then it's going to relax all of the edges that were discovered from the set of sources, and so on and so forth. Then it using the nodes identified in the Bellman-Ford, it builds a directed forest, which is to say that it uses all of the nodes that were identified. It connects all edges that can be connected between them, and it builds a directed forest, which is the union of some trees. And then from the directed forest, it identifies which trees have more than k vertices, and outputs the roots of those trees, which are going to be some source, and these are our pivots. Going towards the time complexity real quickly, the lines 3 to 13 are just Bellman-Ford, and we know Bellman-Ford runs in m times k, where m is the number of edges, k is the number of steps, and since we are working with constant degree graphs, our number of edges can actually be a constant factor more than the number of nodes, which works out to be the way we are doing Bellman-Ford, it works out to be the number of vertices in W, this the lines 3 to 13 can actually run in k times the size of W. Lines 14 and 15 can be done in linear time in the size of the set of nodes W. So then our time complexity becomes dominated by our Bellman-Ford, which then works out to be big O of k times the size of set W.
So now, with our set of sources reduced to a handful of pivots, the next step is going to be very similar to Dijkstra, but since we have multiple sources, then instead of going through them one by one as you would using a heap, what if we process them as chunks at a time? And for this purpose, the paper introduces the block-based linked list, the data structure D. And this data structure D stores key value pairs where the values give priorities, but it also has three special parameters. N is the total number of keys it can have, M is the batch size which it can extract at a time. So while heaps can only extract one element at a time, this data structure can extract M. And B is the max value bound on any value that will be in the data structure. Now you can insert key value pairs into this. You can insert multiple key value pairs in this if all of those have values less than existing values in the data structure. And you can also extract a bunch of keys from this, in fact M keys from this, which have the smallest values. And you also get along with that a value X, which separates the values in S prime from the remaining values in the data structure. And if there's nothing else in the data structure, you get back infinity. Now, the way the algorithm works is that for k, which we already found as log to the 1/3 n, and t is log to the 2/3 n, then the input for the algorithm is that it takes in a level L from 0 to log n by t, where the highest level, the level which it will be called from, is log n by t, ceil. And given a set of sources such that this set size is less than equals to 2 to the LT, and a target upper bound B which you want to achieve, such that for every vertex with distance less than B, the shortest path to that vertex B visits some complete vertex U in S. That means for the sources we have, we can actually find shortest paths through these sources, given that the path length is less than B. Now, the output is supposed to be an achieved upper bound, B prime, and this might actually be B itself. And what this upper bound tells us is that for every vertex with distance less than B prime, you have actually managed to complete those vertices, that our estimate of its distance is the actual shortest path distance. Now, the base case of this algorithm, where L equals to 0, then S is going to be a singleton by the 2 to the LT property. And we can just run Dijkstra from X and complete K vertices, or just complete the boundary itself. And if we go to the pseudocode here, we see what's happening. You take the source as your U0, and then you store it in a heap, and then you just extract the minimum element from the heap and relax it outwards and add and remove from the heap, very similar to how you would do with Dijkstra. And at the end, you either, if you have U0 has K vertices, then there was actually too much work to do, so you may not have achieved your target boundary. In that case, you just return the maximum that you were able to do. But if you actually have less than K vertices, then you know that, okay, you actually met your target boundary and you're good. The other thing to note is that since S is a singleton, we know the shortest paths actually have to start from this specific node. And so every time we're actually processing these distances, we're getting a guarantee that S is the source that we have, the singleton we have is complete, and all the paths we're finding from it are therefore also complete. The recursive case has that, okay, you have a bunch of sources, you first shrink them to a set of pivots using the finding pivots algorithm, and then you initialize your current boundary to the smallest pivot distance that you have. This is because any distance that you will get larger, so any distance that you can compute from here has to start from some source, and so it needs to have at least the distance of the smallest source. And then, while fewer than k times 2 to the LT vertices have been completed, we extract m equals 2 to the L minus 1 t smallest sources. And this is important because this means that on the level just above 0, so at level 1, I will extract only one source, which is why in the base case you always get a singleton. And so you extract 2 to the L minus 1 t sources, and you get the set Si equals to these m sources and the upper bound which separates it from the remaining values in the data structure. And then you try to compute all distances and complete all vertices with distance less than its boundary value, or you just try to get the new achieved boundary that you could using these sources and this boundary. And then once you've found a bunch of complete vertices and you've achieved a certain boundary, now you want to relax all the vertices that you just completed to find new sources which cross that boundary, and then you want to return, and then you repeat this over and over until either you've hit the target number of vertices that you wanted to complete, or there's no more sources that remain, which means you've actually achieved your boundary B. And then at the end you return the updated boundary, whether you met the target or you did not, and the set of all the vertices that you completed within it. And you can see this happen in the algorithm itself. So you find the pivots, you store them in the data structure D, and then while you haven't gotten k times 2 to the LT vertices completed, then you just recursively or repeatedly take the smallest sources that you have, try to expand outwards to the boundary. Then once you've completed some vertices, you try to relax all of the vertices you completed to find new sources. You insert these sources back into data structure D, and then you repeat until you hit your target, or you run out, or you have encountered too many vertices and you have to stop. And then you return your achieved boundary along with the vertices that you completed in this run, along with the vertices you completed in the find pivot section. If we want to try it on this, we can do it on this graph where we have 10 nodes, and so correspondingly t is 2 and k is 1. And we start off with source S, and we try to find pivots, but since it's the only source, that remains the only pivot as well. And then we run Dijkstra on it to find just the node S as complete. And then we relax all of the edges going out of S, and we find the nodes A, B, and C, where A has the smallest value, so that's the next thing we process. Again, running Dijkstra, but only for one step because K is 1. And then we relax the edges from A, we get D and E, and actually D and E both have distances which are less than distances of B and C, so they get put in earlier in the queue. And then we just repeat with then processing D and then processing E. And the last element we took out is E. The value after that was B. B has a value of 7, so we return B prime as 7. That is, we've achieved a boundary of 7 so far. And on the graph, this would look like this, where we have this line for 7. Now, all of the completed nodes, which are S, A, D, and E, we will now, at the higher level, relax them, and we will get nodes, new sources, B, C, G, and H. And we will then pass them down into a recursive call. Now, when we pass them down into a recursive call, we actually get that when we do find pivots, we find that C and H are useless because the shortest path to F comes from B, and the shortest path from I comes through G, and so there's no shortest path leaving H and leaving C. So we can discard C and H. Then we process node B, and we get F in our queue, but it has a value larger than G, so it's inserted later. We process G, then we process F, then we process I, and each of them returning themselves. And actually, the last element we process is I. There's no elements after that, so the boundary we get back is infinity. And we pass this up, and what this means is actually the boundary has reached the end, and we have processed for all distances. We found the shortest path. And the important thing is all of the values in this left half are smaller than all the values in this right half. In fact, the sources in this right half are guaranteed to be at least of size 7. That means that at the same level, if I look at the problem, the nodes that this completes are going to be disjoint from the nodes that this completes. This can help us in our time complexity when we look at the recursion levels and think about how many nodes they're processing.
All right, it's high time we talk about the data structure D that we've been using up until now. So this data structure D is a block-based linked list. It contains two sequences of blocks, D0 and D1. Each block in the sequence contains a linked list of key value pairs, and the order of this linked list does not matter. However, the blocks themselves are stored in sorted order. So a bound is maintained for each block, such that all of the values in the linked list of that block are less than that bound, and all the values in the linked list of the next block are at least as big as that bound. Furthermore, the sequence T0 only stores operation elements that were added as part of the batch prepend operation that we've seen before. Whereas D1 stores elements only added through the insert operations. An integer parameter m denotes the maximum size that a block can be, so that the maximum size that the linked list in the block can be. And the number of blocks in D1 is bounded by n over m, whereas there's no such restriction for T0. These are the amortized complexities for the operations of this data structure. And to illustrate, suppose so this is your data structure. It has two sequences of blocks D0 and D1. Initializing will always, of course, be constant time. If you're inserting, you want to insert, you're going to be inserting into D1. So you need to insert into one block. So some block in D1. So you first identify the right block, which is to say the block such that its upper bound is greater than the bound of the value the value that you're inserting, which can be done in logarithmic time if you store these bounds in a binary tree. And then you can insert it into anywhere in the linked list. You can insert it at the head of the linked list, so there's no additional cost to add it into the linked list. Deleting is constant time, but this is amortized complexity, and the argument is that everything that is inserted is deleted. So the time for delete is accounted for in the insert operation by some constant factor. Splitting occurs when you insert it into a block, the block gets too big, and it has to which means to say size exceeds m, which is the maximum size of a block. That it needs to split into two separate blocks. And using a linear time median finding algorithm, that can be done in the linear time in m. But you still need to update the binary tree, storing the bound, so it becomes logarithmic in n over m. Furthermore, batch prepend is the operation that adds a bunch of values in D0. Suppose the values you're adding is L. If L is less than M, then you can just add and make a block for those values and put it at the start of D0, and then you're done. But if L exceeds M, then you need to call split again. And that's why the complexity turns out to be L times log of L over M. Pull is when you pull out the M least values across both sequences, and using a linear and M algorithm for finding the k smallest value, for finding the M smallest values. They can do this operation in linear time as well. All right. We know the time complexity of the data structure now. So now we are finally able to derive the time complexity of the algorithm itself. Let tau be the recursion tree created by this recursive algorithm. There are log n over t levels in the tree as discussed before. Let x be a recursive call in this tree. It can be shown that for each node x, there will be at most 2 raised to t children, and it follows from the fact that the upper bound on u is k times 2 raised to lt, and the upper bound on ui is k times 2 raised to l minus 1t. So there can be at most 2 raised to t recursive calls. Furthermore, let's define some notation really quickly. Let Sx and Bx be the source set and the bound B given as argument to x, where x is a recursive call. Let Ux and B prime x be the completed nodes U and the achieved bound B prime as returned by the recursive call. Let Px and Wx be the set of pivots and the set of discovered nodes W, respectively returned by the find pivots call in the algorithm, which is at line 3 here. Um, and keep in mind that the size of pivots is at most 1 over k times the size of the nodes in the subproblem, and that the size w the w is is upper bounded by the size of nodes in the subproblem, which is in O of k raised to ld, k raised to 2 raised to ld, where l indicates whatever level x is in the tree. Let SIX be the argument SI to the child node created in the iteration of the while loop in X, and let UIX be the set of nodes UI found by the child node. So it's these SI is this, and UI is whatever is returned here. Then we also know that SIX is less than equal to UIX, which is then in order of k2 raised to l minus 1t. And we also it's shown by the authors that UIX and that for the set of nodes completed by any subproblem are disjoint, and they partition the sets the set of nodes completed by the parent problem. And this also implies that the set of nodes completed at any level in the recursion tree partition the vertex set itself, which means to say if you added up the cardinalities of those of ux for all x at the same level, it would sum up to n. Um, let kix be the set of nodes k that are prepended at the ith iteration in the while loop through the batch prepend call. Okay, we're gonna speed through the time complexity. We're only gonna look into some few function calls because those are the calls that dominate the time complexity, that would dominate the time complexity. Everything else is either constant time or it's negligible. So first we're gonna start off with looking at the find pivots call over here. We know that the find pivots complexity is k times the size of the set W. We know that the size of set W is bounded by the size of the set of nodes discovered in the BMSSP call. So we can write the complexity for find pivots of one call of BMSSP to be k times the size of set of nodes discovered by it. For all nodes in the same layer, we know that ux partitions the vertex set. So if you sum these up across this layer, k can be factored out, all of the ux's sum up, and they cardinality sum up to n. So for all nodes in the layer, that's called the complexity of the find paper is called is k times n. You can multiply this by the number of layer, which is log n over t, and then you can work out the complexity to be n log n to the 2/3. We can look into the insert call, which is adding pivots into the data structure, and the size of pivots can be at most size of ux over k, where ux is once again the size of the set of nodes discovered in discovered by the function call. For one node for one node, the complexity for insertion is n over m, where n is ux over k. And get input set to ux over k. M is 2 raised to l minus 1 t. You remind ux is then k times 2 raised to lt, where k is k and k cancel out, so it turns out to be log of 2 raised to lt over 2 raised to l minus 1 t, and you can work this out to be ux over k times t. Then for all nodes in a layer, you can sum this up. Once again, ux potential over x, so it turns out to be n over k times t. Then for all layers, you can multiply this by log n over t. It works out to be n log n to the 2/3 once again. We can ignore this pull call here because we can argue that in average analysis, the everything that is pulled is first inserted, and we can attribute the cost of pull to a constant factor in the insert call. We'll come to this insert call a bit later. We'll first look into this batch prepend call, which is prepending two things. It's first preparing the set key identified, and it's also preparing a subset of sources. So we know these are subset of sources that were given to the child node, which are the LMS layer. So the subset of sources is at most the size of the nodes discovered at the L-1 layer by the child node. So for one iteration, which is to say for one value for one I in the while loop, this can work out to be so this is at most k times 2 raised to L-1 t. If the L layer is k times 2 raised to lt, this k times 2 raised to L-1 t. And then the complexity for batch prepend is log of log of L over m. So L times log of L over M, where L is this, and then you can work out that L over M, log of L over M works to be log K. Then there will be at most 2 raised to T, 2 raised to T iterations in a node. So for one node, this turns out to be the complexity, where here K times 2 raised to LT is the size of size of UX itself. You can sum this up in a layer. Once again, UX sums out to be N. We can multiply this with number of layers, and then it works out to be N log N 1/3 log of N. We will come to how k is being batch dependent later. Once we're going to move back up to this part. So one insight here is that okay, everything that is so every edge only appears once in a layer because the set of nodes returned in UI are disjoint. So in the same layer, only one edge can only appear once. Furthermore, the condition that this condition can only be satisfied only once in the entire tree. So only edge is processed once in the entire tree, and at once when it's being processed, it does log of it inserts, so it does log of n over m work, where at any layer log of n over m works out to be log of k plus t. So for all layers, the complexity of this operation turns out to be m log n to the 2/3. Now finally coming back to this k that we had before. So k can be at most the size of the number of nodes, can be most in the order of the number of nodes returned by the recursive call here. And for we're going to be batch prepending these, so we can work it out that the batch prepending which batch prepending this many elements works out to be for all nodes in the layer works out to be m log k. Then we can multiply this by the number of layers, it works out to be m log n to the 1/3 log of n. These are our final values for across all layers. So across all of these values, we can see that m log 2/3 n dominates. So at the end, we get our final complexity to be m log to the n to the 2/3. Now we first start off with constant degree graphs, which feels quite limited, and it also quite helps us quite a lot in our analysis. However, it turns out that any graph in fact can be converted into a constant degree graph as follows. First, suppose we're given a graph v comma e. We can construct a new set of vertices v prime such that every vertex in v is substituted by a cycle of vertices that are strongly connected with zero weight edges. And then for every edge UV in the original graph, the vertex X UV exists in this cycle. Then we can construct E prime, a set of new edges, as connecting two vertices, XUV and XVU in the new graph with weight to WUV if the edge U comma V with weight WUV existed in the original set. You can work this out, and then it turns out to be that every node in this new construction has at most 2 integer and out degree, and the shortest paths do not change.
Lastly, we provide some less efficient yet inspired approaches to the same problem. One which we partly discussed earlier is to just keep dividing until the problem size is of one node, instead of just stopping when the problem size is k nodes. Now, this is very interestingly the same as Dijkstra by itself, but it's really cool to see another way to get at that solution. Another creative but a slower approach is that in the base case for a BMSSP, we, instead of using Dijkstra, use Bellman-Ford. Now, the only issue is we need to complete k nodes, so we need to relax k times, and that can be a bit expensive. But that covers it for this presentation. Thank you for listening, and I hope it helped. Bye.